Alright, so here we're looking at a mixing problem. We have a tank, 100 kilograms of salt, and 2,000 liters of water. So I'm going to actually write that down in my little picture here. 2,000 liters of water and 100 kilograms of salt. And what else? So a solution of a concentration 0.025 kilograms of salt per liter enters the tank at a rate of 7 liters per minute. So we know, if you see this picture, we got something going in, and it's entering the tank at 7 liters per minute. And I'm also going to actually write this concentration because it also has 0.025 kilograms of salt per liter. That's entering the tank, and the solution is mixed and drains from the tank at the same rate. So we know that this well-mixed solution is also draining, and that's what that little pipe represents. And it's draining at the same rate. So the same rate that is draining is 7 liters per minute. Right? It's entering the tank at 7 liters per minute with this salt concentration. And it's leaving the tank also at 7 liters per minute. We also are given kind of our variable here. Y is going to represent the number of salt in the tank after T minutes. So essentially, if we're going to solve this equation, we would get a y of t function type thing. And it also helps with our differential equation to set this up. We know we are going to be looking at a rate, because the rate of salt entering and leaving at a certain time. And I basically said what the equation should look like. It's going to be the rate salt going in minus the rate salt going out. And I mean, that's essentially how we're going to get our differential equation. Some side work, just because we have the equation up above. I'll do some scratch work here. Looking at the rate in, we know that 0.025 kilograms of salt per liter is going in. So we know 0.025 kilograms per liter is going in. But also, we essentially want the rate the salt is going in terms of it's going to be kilograms, because that's what Y represents, and over time. So kilograms per minute. We don't want kilograms per liter, we want kilograms per minute. So to fix that, we just need to convert this, and we know it's entering at 7 liters per minute. And what's nice about that is the liters will cancel out, and we are left with our kilograms per minute like we want. And that's it, right? So that's actually the rate going in. We can write that, but I am going to do the rate out next. In a similar process, we know we want the rate out has to, again, be in terms of kilograms per minute, And we do know it's leaving at the same rate. The fluid is leaving the tank at the same rate, which is 7 liters per minute. And again, we want to essentially look for the rate that the salt is going out. So we need to convert that to, again, kilograms of salt per liter, or per minute. And that gives us part of it because we know we want kilograms of salt, so we're going to need y of t because that's in terms of how much salt, right? So y is the number of the kilograms of salt. So then that's going to be out of the total volume of the tank, right? Because again, we are going to want to cancel the liters, and we're going to need to get liters as the volume, right? And that is 2,000 liters in the tank. Just a small side note, because in general, you don't always have the same rate leaving in and out. What you really are doing is the volume of plus the difference in the actual rates. So you know the rates going in is 7 liters per minute and also going out. But a lot of times you don't have that case. It's different. So, and of course that's as time is going on, so it would be multiplied by time. But the nice thing for us is this is 0. So ultimately we have our the information we need. And again, the liters cancel out here. This is going to end up being in liters, and we have for both kilograms per minute, and that will be our differential equation. So the rate that the salt is going in the tank is going to be 0.025 minus, oops, I forgot the 7, the times 7. Let me get rid of that real quick. It's going to be 0.025 times 7 minus the rate going out, which is going to be 7y over 2,000. And that is our differential equation. Let me try to box that one more time. Of course, you can multiply the .025 times the 7 out. Also, last thing, we also were given an initial condition that at time 0, or initially, there is 100 grams of salt, right? Sorry, kilograms of salt. And that would be it. And we could totally solve this. We can solve this differential equation either by separable or integrating factor. You can do that if you like, or leave it as is. Thank you.